Assalamualaikum, hi everyone. So this is a video for chapter 5 hydrocarbon. In this video, we're going to discuss on subtopic 5.2 alkenes, and at the end of this lesson, you should be able to describe the preparation of alkene through dehydration of alcohol and dehydrohalogenation of haloalkenes. Then you should be able to justify major product formed using the Zaitsev rule and predict the major product of elimination reaction. Preparation of alkenes. So this is the general structure of our alkene, where we have the functional group of carbon-carbon double bond. And to prepare our alkene, there is two ways. The first one is by dehydration of alcohol. Okay. So for dehydration of alcohol, the reactant needed is the alcohol itself. So if you look over here at the carbon-carbon double bond that will form, at the carbon-carbon single bond over here that will form the carbon-carbon double bond, it is bonded to hydrogen and also an hydroxyl group. So what are the conditions for dehydration of alcohol? So to change alcohol to become an alkene, we need a concentrated H2SO4, or we can use other strong acids. But usually we're going to use concentrated H2SO4, and it must be concentrated and stated as concentrated. And then the reaction must be done with heat or under reflux. So these two conditions must be shown here on the arrow. So on the reaction arrow over here, you're going to put concentrated H2SO4. It's compulsory to have the concentrated in front. And this triangle sign to show that it is heated under reflux, or heat or reflux. Or if you don't want to put the triangle sign over here, you can just simply write it down as heat, or you can also write down as reflux, as long as it shows that there is source of heat. Okay, so what will be the product? So from here, the product that you will get is an alkene. Okay, of course, the alkene that we want to produce. And also, we eliminate H2O. So the H and OH over here will be eliminated to form H2O. So that will be dehydration of alcohol. So like I mentioned before, we have an elimination of H2O from the alcohol compound. So the next one, we have dehydrohalogenation of haloalkene, or we also call our haloalkane as alkyl halide. So the reactant needed, obviously, we need our haloalkane over here, or we call it also as alkyl halide, where we have here HX. Rx over here, R correspond to your alkyl group and X is the halogen. So if you look and compare between the alkene that we want to produce and the reactant, which is our haloalkane, at the carbon-carbon single bond over here, we have hydrogens and X, our halogen. Either we use bromine or chlorine. So the conditions for dehydrohalogenation of haloalkane is, first, we must have base. So the common base that we're going to use is KOH, or we can use any strong base. And then the reaction must be in alcohol medium. So we must put a trace of alcohol in our reaction. And then the reaction must be done with heat or under reflux. Okay, so this is how you write down the the condition on the arrow. So we must have our base with ethanol under reflux. So the product that we will get over here, so obviously we're going to get our alkene, and then we have KX. KX over here is actually the salt plus water. So in dehydrohalogenation of haloalkane, to form the carbon-carbon double bond, what we did is we remove H and X from here. Okay, in other words, the elimination of HX from the haloalkane. So in general, for these two reactions, for preparation of alkenes to produce a carbon-carbon double bond, the type of reaction will be elimination reaction. In a reaction to form alkene, in one reaction we might get a mixture of product, a mixture of alkenes. So when we have a mixture of alkenes, we need to determine which one is the most stable alkene. And to do so, we're going to use Zaitsev rule. What does Zaitsev rule state? It says that in an elimination reaction, the major product is the most stable alkene. Okay, how do we determine that it is the most stable alkene? Commonly, the most highly substituted alkene. So, when we talk about over here, most highly substituted alkene, substituted with what? So here, the substitution is referred to our alkyl group. Okay, so if you look at here on this table, here we have ethene. Ethene, when you have a carbon-carbon double bond bonded to only hydrogen. Each restricted carbon over here only bonded to hydrogen. So when we substitute one dihydrogen with an alkyl group, so the stability of that alkene will increase. So as you can see over here, once all the carbon at the carbon-carbon double bond is substituted with an alkyl group, the stability will increase. So this structure is the most stable alkene. Okay, now let's look at one example. So we have an alcohol over here. So the name of this alcohol, okay, so 1, 2, 3, 4. We have an hydroxyl group over here and a methyl group. So the name will be 4 is for butanol. So 2-methyl, 2-butanol. Okay, so that's the name. So let me erase this. Now we react this butanol, okay, with concentrated H2SO4 and then we heat. So the product that you will get, okay, over here we're going to produce our alkene. Okay. Now, how do we know which bond is the one that is involved in the elimination process? So first, focus on where is the hydroxyl group, because you know we're going to remove this. Okay, so and then after OH, we're going to remove one hydrogen. Okay, so where can we get the hydrogens? So let me change this, H2. Okay, the possibility is one is over here and the other one is over here. Okay, so this one, just now I change it to CH2. Okay, because I opened the bond over here. Okay, let me draw it upwards so you can see the bond. Okay, so we're going to eliminate OH over here, and if let's say you remove the hydrogen over here, the carbon-carbon double bond will form here. And if let's say you remove OH with the hydrogen over here, the carbon-carbon double bond will form here. Okay, so in other words, we will have two products over here. Okay, so these are our products. So if you look over here, we have first 2-methyl, 1-butene, and then we have 2-methyl, 2-butene. Okay, so which is which? So if we remove OH and then we remove the hydrogens on the left hand side, the blue hydrogen over here, the product that you will get is this one. Okay, it's 2-methyl 1-butene. Okay, but if we remove the hydrogen, okay, on the third carbon over here, so let me number our carbon. So carbon number 1, 2, 3, and 4. Okay, so here is 1, 2, 3, and 4. Okay, and then this is carbon number 1, 2, 3, and 4. Okay, so if you look closely over here, so this is the product when we remove this hydrogen and hydroxyl group, and 2-methyl 2-butene is the product when we remove the hydroxyl group with the hydrogen in the green circle over here. Okay, so now we want to determine which one of this structure is more stable, is the major product. So we're going to focus on the alkyl group. So for 2-methyl 1-butene, it has 2 alkyl groups over here. Okay, because this carbon is bonded to 2 hydrogens and 2 alkyl group. While for 2-methyl 2-butene, it is bonded with 3 alkyl group. At the carbon-carbon double bond over here, bonded with 3 alkyl group. So if we refer back to the Zaitsev rule over here, so which one will be the major product? So the major product, the most stable alkene, will be the one with highly substituted alkene. Highly substituted with alkyl group. So this is our major product. 2-methyl 2-butene is the major product, and 2-methyl 1-butene will be the minor product. So, if you are still a bit unsure on how to draw your alkenes and to choose which one is the major or the minor product, worry not, we're going to discuss it further in our tutorial during the mechanism of dehydration of alcohol to produce the alkene. So with that, this will be the end of this video. Thank you.